Welcome everyone to Guided Study Group Week 7 of Math 140. And so, hopefully everyone have like a wonderful midterm week, and you guys have done a great job on like the previous type of material. So today we're gonna continue with materials for exam 2. So, it's going to be based a lot on derivative and how to use derivative, both the first and the second derivative in graphing, and how to construct a graph with all of the features that we need, like maximum, minimum, concavity, inflection point, and all of that. So the first thing is section 2.9. So section 2.9 is the one that kind of like a little bit kind of like a small application of derivative. It's based on linear approximation and tangent line approximation. So it's kind of like allow us, the entire point of doing linear approximation is allow us to find the approximate value of a function without using calculator. So say if we have like a function like square root of x, and we want to find what is the value of square root of 1.01. If we don't have the calculator, there should still be a way that we can estimate this number on site. So this is also like one of the most important features of industrial jobs, is that most of the time you're going to be paid to be able to estimate something immediately. And so this is one of the ways that we're going to do it. So linear approximations say that you're going to have the approximate value is going to equal to a close by value. So say fa, say if you have square root of x, and you want to find square root of 1.01. So f of a is going to be square root of 1. So kind of like find a nearby value that's easier to find. And then you approximate it using like a tangent line part. So using a tangent line approximation. So this is you see a tangent line with the slope, and then you have this part. Now there are some part about over and underestimate. So say if you have a function, and so this is more dealing with the graph. So say if you have square root of x, the graph is going to be like y equals square root of x. So x is going to equal, so it's going to be like this. So say if you want to find a point here, a tangent line, which is going to be so this is at 1, say this is easier value, this is at 1.01. So a tangent line like this, tangent line approximation, this one is going to be overestimate, because the estimate value based on this graph is higher than the actual value. Let me zoom that part bigger. See, like the approximate value is here, but this is approximate. This is actual value. And so this is an overestimate. The same thing if you have like a graph like this, and this is a tangent line, and then you have 2 points. So this is actual value, and this is approximate. Then this is an underestimate, because the estimate value is smaller than the actual value. So it's kind of like just graph wise, and kind of like understand exactly where our estimate are compared to the actual value, like how bigger, how smaller, and all of that. So some of the type of problem you'll be asked in this question is use a linear approximation to estimate something. And so usually that is a function, but like square root or some sort of root or so on, it's going to be hard to compute directly, and say if you don't have a calculator there. And so what you're going to do is the first step is identify what is fx and the value of a. And so say this is all based on the problem. So say if you ask, hey, find cubic root of 3.2, then fx is going to be cubic root, and the value of a, it can be 3, it can be 4, it can be any nearby value that we already know the cubic root value. Apply the equation of linearization. So apply equation 1 into it. For y value of x, another problem is for y value of x is the linear approximation within M. And so this is when you're also doing the same thing, identify f of x. And so now you have to solve for x, knowing that the absolute value of fx minus lx is smaller than m. And this lx is based on this equation. So from equation 1. So when you have fx is a function that you just identify, lx is this from equation 1. So you just solve for x from this part. Now let's go to example 1. We still have differentials. So differential is kind of like another way to like represent the linear approximation, where you have so say if you have a graph, the same thing, instead of just doing the tangent, now you're letting this point get really close to the easy point that we have. So when you have delta x approaching 0, so that is the one. So in Lx we have f of a plus f prime of a times x minus a. So this is the part we call delta x. So say if we have delta x approaching 0, so this the main point get really close to the inner part. What are we gonna have? How do we do the estimation? So the way that we're gonna do that is that now we're gonna have dy equal f prime x dx. Also, we have the approximate value is approximately fa plus dy. Essentially, in representation and meaning-wise, it's the same thing. So we're gonna have the same type of problem with linear approximation. So it's just the way that they represent it. Instead of in the tangent line form, you put it into this form, and it's the same thing. But this one is usually when you are asked to find maybe there's another type of problem that you can be asked, is that find the general equation of the approximation. So in that case, your answer will not be a number, it will be like a function with respect to x. And you can just base on this and do the questions. Now it's easier gonna be looking at the example 1. So example 1 is question 38 of this section in the book. It's say you want to have blood flows along a blood vessels. The flux is proportional to the fourth power of the radius. So the flux is proportional to the fourth power. So it's going to equal kr fourth. Show that the relative change in F is about 4 times the relative change in R. How will a 5% increase in the radius affect the flow in blood? And so, to do this, we're gonna do linear approximation. So you want to find the relative change in F. How does it relate to the relative change in R? And to do that, we take derivative of both of them. So we have df is going to be take derivative with respect to f. So it's going to be 4k r cubed dr. And so now we have relative change. Relative change is called the change with respect to itself. So we're gonna have df divided by f. So we divided this entire thing by this entire thing. So we have 4k r cubed multiplied dr over r. You have k r cubed. So what we end up having is going to be 4 dr over r, and this is what we're supposed to prove. So we're supposed to prove that this relative change in f, this is relatively change in f, is 4 times relative change in R. Now, how will a 5% increase in radius affect the flow in blood? So when we have dr over R is equal to 5%, then we have df over f is going to be approximately 20%. So this is kind of like everything is estimation, but we're using the basis of linear approximation to estimate the relative change in f when radius is increased by 5%. So when in the exam you ask a questions like about something that you cannot see directly related to math, so say how like a relative change of this related to this, like in physics, biology, or econ, then that's one of the things that will give you the hint that you have to use linear approximation. But in this case, like the use of linear approximation is kind of subtle, so just be aware with that and kind of like do a lot of practice. Try to put yourself in the scenarios that you have to like practice with the problem in the book. I would say, especially the one that's in like a work problem like this. A work problem like this, then that'll be more helpful. So having said that, that's all I have for section 2.9. Now we're gonna continue with 3.1. So 3.1 is when we go in deep into the use of derivative to find minimum, maximum, and then we have on an interval of a function. So some definition. So in this sections, what you need to know is the definition of absolute maximum and absolute minimum. So absolute maximum is kind of like the maximum on the entire domain of a function. So say if you have a function like this, so the domain may be starting from 0 to this point A. So when you have a function like this, so the absolute maximum is going to be up here, and the absolute minimum can be down here. So it's on the entire domain. Then we have local maximum and local minimum. So these are the local maximum. So it's the peak in its local region. So it's in like a relatively small interval in the domain. And these are the local minimum. So extreme values. Extreme values is when we define extreme value as the maximum or minimum, but not at the end point of an interval. So this is the absolute maximum, but it is not an extreme value. This usually it's not considered extreme value. Then we have critical number, and this is really important. So critical number is defined as a number C in the domain of F. So in domain of F, such that either you have f prime of C equals 0 or f prime of C does not exist. So, and usually at critical number, if you have a local max or local min at C, then C is definitely a critical number. However, the way back is not correct. So when C is a critical number, it can be a maximum or minimum or nothing at all. And the reason is that you're going to see in a few minutes. So one of the ways that we're going to find what is the critical number of a function on, like, say on an interval, is that you have to find what is f prime of x and set it to equal to 0 or find where the point where it doesn't exist. Then we have something called the extreme value theorem. So extreme value theorem is allow us to find kind of like make sure that if you have kind of like ensure us the fact that you're going to have a maximum and a minimum on an interval of any kind of function if a function is continuous. So if f is continuous on a growth interval from A to B, then f attains an absolute max and an absolute mean at some number C and D in A and B. So it ensures us the fact that for any continuous function on an interval, then there will always exist an absolute maximum or an absolute minimum. Fermat's theorem. So next we come to Fermat's theorem, is saying if you have a local max or a local min at C, and if f prime of C exists, and you have f prime of C equal to 0. Now be careful. As I said, you do not just put f prime of x equal to 0 and solve for, because in those cases you can miss some solution. Why is that the case? So say if you have a function, say fx is equal to square root of x. So x equals 0 is in the domain of f. However, when you take f prime of x over 1 square root, then f prime of x does not exist at 0. But when you draw the graph out, that is the absolute minimum. So do not just set it at 0 and then you're gonna miss the solution, because just like one of the example that we show. Then we have finally one very important one as well, and this is going to be the main part of this section, is the closed interval method. So the closed interval method allows us to find the absolute maximum and absolute minimum values on a continuous function on an interval. So what we're going to do first step is find all the critical value, all of the critical numbers. And to do that, we either set f prime equal to 0, or we have f prime does not exist. Then we find all the values of f at the critical number. Then you find the values of f at the endpoint. So say if you have here, you find these critical numbers c, then you find f prime of c, fc here, and you have find fa and fb. And then among these numbers, which one is the largest one is the absolute maximum, and the smallest one is going to be the absolute minimum. So it's just the way that you not only just account for the critical number, but you account for the endpoint, because we're talking about absolute maximum and absolute minimum, and it's not just a local one. Now, let's go to the first example of this section and see how it works. So find all the critical number. Again, first thing, you have to identify what is the domain. So domain of this is R, because this is cubic root, and so the expression inside cubic root, it doesn't have to be positive or equal to 0. So the way that we did that is, now we can, let's just find g prime of x. G prime of x is 1/3 over 4 minus x squared to the 2/3 multiply negative 2x. So it's going to be negative 2x over 3 multiply square root of 4 minus x squared. Now, when you find a critical number, two things. You have to set first g prime of x equal to 0 and g prime of x does not exist. So when it's equal to 0, x is equal to 0. That's when you have the numerator have to equal 0 and denominator different than 0. Obviously, when you have x equals 0, denominator is different than 0. So that works. Now, when you find it does not exist, you have to find where you have 4 minus x squared equal to 0. Or you have x equal to 2 or x equal to minus 2. So we have all critical number are negative 2, 0, and 2. So that's the step you're gonna do if you were asked to find all of the critical number. Now go to the next example. Find the critical number of this. This is when you have to be careful, and always the first step is to identify the domain. Here you have this one is cubic root of x minus 1 over cubic root of x squared. So the domain here doesn't include 0. So when you find g prime of x, you have 1/3 of x to the 2/3 minus plus 2/3 x to the 5/3. And so critical number, you set g prime of x equal to 0, or g prime of x does not exist. Now we're going to put them in the same denominator, make it easier to find. So you're going to have x plus 2 here. So when you set that equal to 0, you have x plus 2 equal to 0, or x equal to negative 2. And so at x equal to negative 2, the denominator is different than 0, so that works. When g prime of x does not exist, this one does not exist when x equal to 0. However, we have to make sure the fact that x equal to 0 have to belong in the domain. But here it doesn't belong to the domain at all. So our conclusion is that the critical number are just x equal negative 2. Because this is belonging to the domain, but this one does not. And so when you're talking about a function, and the domain doesn't even account for that point. So when you're looking for the critical number, that critical number, if it doesn't belong to the domain, that doesn't really mean anything, because the function itself to exist doesn't account for that point already. So I just want to make sure that the very important part here is in every question they're asking you to find a critical number. Make sure that you find the domain first. Now we have to go to the final example. It's when we started to use the closed interval method to find the absolute maximum and absolute minimum of a function. So the step, as I say, we first find all of the critical number, find the values at the critical number and values at the edges. So say you have fx. Now find all of the critical number. So you have negative 2 sine t plus 2 cosine 2t. And now this one exists everywhere, so you don't need to find where you have f prime of x does not exist. So you can just set it equal to 0 and find where you have sine t equal to cosine 2t. So here is when we have to use the double angle formula to solve this. We have sine t is equal to 1 minus 2 sine square t. And so you have 2 sine square t plus sine t minus 1 is equal to 0. Therefore, you have two parts. Sine t equal to that. Sine t equal to half, or sine t equal to negative 1. Now, looking at, now you know have the two solutions, but look at the interval. Again, this is kind of like instead of a domain, they give you an interval, and you have to make sure that your critical value is in that part. So you have this part. So from 0 to pi over 2, your psi is here. So it's going from psi, it's going from, so when you have t belong in 0, pi over 2, you have your psi t will belong to 0 and 1. So this part, when you have psi t is equal to negative 1 as one of the critical value, you can ignore it because it doesn't belong in the interval that we're talking about. And so by the special angle in the book, you can find that t is equal to pi over 6 when you have psi t equal to half. And so that is our critical number. Now we look at f So find the value at the critical number. So f of pi over 6 is equal to 2 square root of 3 over 2 plus sine of pi over 3, which is going to be square root of 3 plus square root of 3 over 2. This is just going to be 3 square root of 3 over 2. Now at the edges, you have f of 0. F of 0 is going to be 2 plus 0, so it's going to be 2. And then you have f of pi over 2 is going to be 0. So from here, we have three values that we need to compare. 3 square root of 3 over 2, 2, and 0. So our conclusion is that absolute minimum at x equal pi over 2 and min of f is 0. So what we're saying here is that we have absolute minimum at x equal pi over 2 and that minimum equal to 0. Similarly, we have another conclusion for absolute maximum at x equal pi over 6. Max of f is 3 square root of 3 over 2. So that is my final answer for this question. So just make sure that you understand and know the step of the closed interval method, because it's really important in this section and in the following part where you need to find when you eventually put everything together in section 3.5 and kind of like do like accumulative problems on constructing the graph with all the features that we need. Now, having said that, if there's no more questions, try the practice problem in section 2.9, number 6. I found it's not in the suggested problem. I think it's really, really helpful. And so I'll end the section here. Thank you for coming out here, you guys, and then I'll see you guys next week.